The miracle in your glass. Why water is the strangest substance in the universe. Right now, there's a substance sitting on your kitchen counter, flowing through your pipes, and making up 60% of your body. And it breaks nearly every rule of chemistry and physics known to science. You drink it every day without a second thought. You bathe in it, cook with it, and would die within days without it. Yet if you sat down with physicists and walked through its properties one by one, they would tell you that this substance should not behave the way it does, that it is, by virtually every measurable standard, one of the most abnormal and bewildering materials in the known universe. That substance is water. Plain, ordinary, transparent, tasteless water. H2O. Two hydrogen atoms bonded to one oxygen atom in a tiny V-shaped molecule, so simple that children learn its formula in elementary school. And yet, that simplicity is one of the greatest deceptions in all of nature, because behind the humble appearance of water lies a labyrinth of bizarre physical behaviors, quantum-level mysteries, and cosmic significance so profound that some researchers have flatly stated that if water behaved like a normal liquid, life on Earth would never have existed. This is not hyperbole. This is not poetic exaggeration for the sake of a dramatic opening. This is a considered conclusion of scientists who have spent decades studying the anomalies of water and who continue, to this day, to be confounded by them. The number of documented ways in which water deviates from the expected behavior of a substance with its molecular weight and composition exceeds 70 distinct anomalies. And that number keeps growing as new research uncovers still more peculiarities lurking in every drop. So let's begin with something you have seen 1,000 times and never questioned. Something so familiar that it seems absurd to call it strange, and yet something that, when you truly understand what is happening, will make you look at your next glass of iced tea with entirely different eyes. Take a glass, fill it with water, and drop in a few ice cubes. They float? Of course they float. Ice always floats. You have seen it your entire life. In every cold drink, in every frozen lake, in every winter scene you have ever witnessed. But stop and consider this from the perspective of basic chemistry. When you cool down virtually any substance in existence, its molecules slow down, pack together more tightly, and the material becomes denser. The solid form of almost every known substance is heavier than its liquid form. If you were to freeze olive oil, the solid olive oil would sink to the bottom of a container of liquid olive oil. If you were to freeze molten iron, the solid iron would sink in the liquid iron. This is the normal, expected, unremarkable behavior of matter in our universe. Solids are denser than liquids, period, except water violates this rule in spectacular fashion. When water cools down from room temperature, it does initially behave normally, its density increasing as the molecules slow and move closer together. But something extraordinary happens at around 39 degrees Fahrenheit. At that temperature, water reaches its maximum density, and then, as it continues cooling below that point, it begins to do something that almost no other substance does. It starts to expand. The molecules begin arranging themselves into a crystalline lattice structure, a beautifully ordered hexagonal framework, and this framework contains gaps, empty spaces between the molecules, like a scaffolding with open windows. By the time the water has fully frozen at 32 degrees Fahrenheit, it has expanded in volume by roughly 9%, making the solid ice significantly less dense than the liquid water it just came from. And so the ice floats. It rises to the surface of your glass, bobs her cheerfully, and you think nothing of it. But what you are witnessing is one of the most consequential anomalies in all of physics. Because if ice did not float, if it behaved like the solid form of nearly every other substance and sank, the consequences for our planet and for life itself would be catastrophic beyond imagination. Picture a world where ice sinks. It is winter in the northern latitudes, and the temperature drops below freezing. The surface of a lake begins to freeze, as it does in our world. But instead of forming a protective sheet on top, The ice, being denser than the water below, immediately sinks to the bottom. Fresh liquid water is now exposed at the surface, and it too begins to freeze. And that ice also sinks. Layer after layer, the lake freezes from the bottom up. By the end of a long, harsh winter, the entire body of water is a solid block of ice from the lake bed to the surface. Now spring arrives and the sun begins to warm the land. But sunlight can only penetrate so far into a mass of ice. The surface begins to melt, but the deep ice, insulated by the water above it, remains frozen. Summer comes and goes, and still the bottom layers never fully thaw. Year after year, more ice accumulates at the bottom. Over decades and centuries, lakes and rivers become permanent ice blocks. The oceans, too, would gradually freeze from the bottom up in the polar regions. And those frozen depths would never see enough warmth to melt. In such a world, aquatic ecosystems as we know them would be impossible. Fish, plankton, algae, the entire food web of freshwater and marine environments would be wiped out or would never have evolved in the first place. The implications cascade outward from there because the oceans regulate climate, drive weather patterns, and cycle nutrients across the globe. A world with sinking ice is a world that lurches toward total glaciation, a snowball planet locked in perpetual cold. But that is not our world because ice floats. In our world, when a lake freezes in winter, the ice forms a protective lid on the surface. This lid insulates the liquid water below, preventing it from freezing solid. Beneath that frozen ceiling, the water remains liquid, hovering around 39 degrees Fahrenheit, the temperature of its maximum density. Fish swim in these cold but livable waters. Microorganisms persist. Aquatic plants survive in a state of dormancy. The ecosystem endures, waiting for spring, when the ice will melt from above and the cycle will begin again. This is not a minor convenience. This is a planetary life support system. And it exists entirely because water has an anomalous density curve that makes its solid form lighter than its liquid form, a property shared by almost no other substance on Earth. And the strangeness of water's density does not end there. In recent years, researchers have been exploring the possibility that liquid water itself can exist in two distinct forms simultaneously, a low-density liquid and a high-density liquid, and that under extreme conditions of supercooling and high pressure, these two forms can actually separate from each other like oil and vinegar in a bottle of salad dressing. This hypothesis, sometimes called the liquid-liquid critical point theory, suggests that at temperatures far below the normal freezing point, in a regime where water can be supercooled without crystallizing, the molecular arrangement of H2O diverge into two populations. In the low-density form, the water molecules maintain an open tetrahedral arrangement, each molecule bonded to four neighbors with generous space between them, resembling the structure of ice. In the high-density form, an extra molecule has been crammed into the framework, squeezing into a space where it does not quite fit, creating a more compressed and heavier version of liquid water. If this theory is correct, and computer simulations have provided compelling evidence that it is, then the peculiar density behavior of water at everyday temperatures, including the famous density maximum at 39 degrees Fahrenheit, may be a subtle echo of this deeper duality, a shadow cast by the two hidden faces of liquid water bleeding into each other across the temperature spectrum. The idea that a single substance could harbor two fundamentally different liquid identities is extraordinary, and it is a reminder that even something as seemingly simple as a glass of water contains depths of complexity that science is still working to fathom. Now, let us turn to another of water's remarkable violations of normalcy, one that has consequences just as vast as the floating ice phenomenon. Water boils at 212 degrees Fahrenheit at sea level. You know this. You learn it in school. You use it every time you cook pasta. And it seems like the most unremarkable fact in the world. But it is, in fact, deeply strange. To understand why, you need to consider water's place in the periodic table and compare it to chemically similar molecules. Water is a hydride of oxygen, meaning it is an oxygen atom bonded to hydrogen atoms. Oxygen belongs to a group of elements in the periodic table that includes sulfur, selenium, and tellurium, and each of these elements forms its own hydride. Hydrogen sulfide, the gas that smells like rotten eggs, is a hydride of sulfur. Hydrogen selenide is the hydride of selenium. When you look at the boiling points of these related compounds, a clear trend emerges. Hydrogen telluride boils at about -4 degrees Fahrenheit. Hydrogen selenide boils at about negative counterpart Fahrenheit. Hydrogen sulfide boils at roughly -76 degrees Fahrenheit. The pattern is clear. As the central atom gets lighter, the boiling point drops. Following this trend, water, with its very light oxygen atom, should boil somewhere around -100 degrees Fahrenheit, or even lower. It should be a gas at room temperature, a faint vapor drifting through the atmosphere, utterly incapable of pooling into oceans, rivers, or lakes. And yet, water does not boil until 212 degrees Fahrenheit. A staggering deviation from predicted value, an anomaly so extreme that it demands an explanation. That explanation, as we will explore shortly, lies in the extraordinary molecular bonding that occurs between water molecules. But for now, simply absorb the magnitude of what this means. If water behaved according to the expected trend, if it boiled at a temperature somewhere below the freezing point of the water we know, then every drop of liquid water on Earth's surface would have evaporated into the atmosphere billions of years ago. The oceans would not exist. Rivers and lakes would not exist. Rainfall would not exist. The planet would be a dry, barren rock with a steamy atmosphere, and the chain of chemical events that led to the first living cell would never have occurred. The fact that water remains liquid across such a wide temperature range, from 32 degrees to 212 degrees Fahrenheit, a span of 180 degrees on the Fahrenheit scale, is not just a convenient property. It is the foundation upon which the entire biosphere rests. Consider, too, what this means in the context of our solar system. Venus, Earth's near twin in size and composition, was likely once home to liquid water. But Venus orbits closer to the Sun, and as temperatures rose, the water on its surface evaporated. Water vapor is a potent greenhouse gas, and the accumulating steam in Venus's atmosphere trapped more and more heat, driving temperatures higher, evaporating more water, in a runaway greenhouse effect that ultimately stripped the planet of every last molecule of surface water. Today, Venus is a hellscape with surface temperatures above 850 degrees Fahrenheit. Its atmosphere a crushing blanket of carbon dioxide with not a drop of liquid water to be found. Mars tells a different cautionary tale. The red planet has water, locked in ice caps at its poles and frozen in its subsurface oil. But Mars is small, and its gravity was too weak to hold on to a thick atmosphere. As the atmosphere thinned over billions of years, the atmospheric pressure dropped so low that liquid water became physically impossible on the surface. At Martian atmospheric pressures, water transitions directly from ice to vapor without ever passing through a liquid phase, a process called sublimation. Any ice exposed on the surface of Mars simply evaporates into the thin air. Earth sits in a sweet spot, warm enough for water to remain liquid, but not so hot that it boils away, with an atmosphere thick enough to maintain the pressure needed to keep water in its liquid state. But even this sweet spot would be meaningless if water did not have its anomalously high boiling point. If water boiled at the temperature predicted by its molecular weight and chemical family, even Earth's temperate climate and comfortable atmospheric pressure would not be enough to keep it liquid. We owe the existence of our oceans, and therefore our existence, to the fact that water stubbornly refuses to behave like a normal substance. Let us continue peeling back the layers of water's abnormality, because its thermal properties extend far beyond its boiling point. Water has an extraordinarily high specific heat capacity, which is the amount of energy required to raise the temperature of a given amount of substance by 1 degree. In plain terms, Water takes a tremendous amount of heat to warm up and releases a tremendous amount of heat as it cools down. You experience this every time you boil water on the stove and wonder why it takes so long compared to heating oil in a pan. You experience it when you go to the beach and find that the ocean water is still cool in early summer, even though the air has been warm for weeks, and still warm in early autumn, even though the air has turned crisp. The ocean is slow to heat and slow to cool because water clings to its thermal energy with remarkable tenacity. This property has planetary scale consequences that are difficult to overstate. The oceans cover roughly 70% of Earth's surface, and they act as a colossal thermal buffer, absorbing heat from the sun during the day and during summer, then releasing that stored heat slowly during the night and during winter. Without this buffering effect, the temperature differences between day and night will be savage. The sunlit side of the planet would roast while the dark side would freeze. Much like the surface of the moon, which has no water and no atmosphere, and where temperatures swing from over 250 degrees Fahrenheit in direct sunlight to nearly minus 300 degrees Fahrenheit in shadow. Earth's climate is temperate and relatively stable because the oceans moderate it. And the oceans can moderate it because water has an abnormally high capacity to store thermal energy. Since the 1970s, the excess heat trapped by greenhouse gases in Earth's atmosphere has been accumulating not primarily in the air, but in the oceans. The water has been quietly absorbing this thermal burden, slowing the pace of atmospheric warming and buying time, though at the cost of rising ocean temperatures that bring their own set of ecological consequences. But the fundamental point stands. Water's ability to soak up and store heat is one of the primary reasons Earth's climate has remained within a range hospitable to life for billions of years. Closely related to specific heat is another thermal property where water excels to an almost absurd degree, and that is its latent heat of vaporization, the amount of energy required to convert liquid water into water vapor. When water evaporates, it absorbs an enormous quantity of heat from its surroundings, roughly 1,000 BTUs per pound, far more than most other common liquids. This is the principle behind one of the most vital cooling mechanisms in both human biology and planetary climate. When you exercise on a hot summer day and your body begins to overheat, your sweat glands excrete water onto the surface of your skin. As that thin film of sweat evaporates, it pulls heat away from your body, cooling you down. This is not a luxury or a minor convenience. It is a survival mechanism without which humans and many other mammals would be unable to regulate their body temperature and would overheat and die during any sustained physical exertion in warm conditions. The efficiency of this cooling system depends entirely on water's exceptionally high latent heat of vaporization. If sweat were made of a liquid with a lower latent heat, the same amount of evaporation would remove far less heat, and our bodies would need to produce far more sweat to achieve the same cooling effect, an impossible demand on our hydration and metabolism. On a planetary scale, the evaporation of water from the oceans serves as a gigantic air conditioning system. When the sun beats down on tropical seas, the surface water absorbs the solar energy and evaporates. This evaporation carries vast quantities of heat away from the ocean surface and into the atmosphere, where the water vapor rises, cools, condenses into clouds, and releases the stored heat at higher altitudes. The clouds themselves then reflect incoming sunlight back into space, providing an additional cooling effect. This cycle of evaporation, cloud formation, and precipitation is the engine that drives weather and distributes heat around the planet. And it functions as effectively as it does because water's latent heat of vaporization is so extraordinarily high. But we are still not done cataloging water's defiances of chemical normalcy, because water also possesses an unusually high surface tension, another property that has profound consequences for life. Surface tension is a tendency of a liquid surface to behave like a stretched elastic membrane, resisting penetration and minimizing its surface area. Among common liquids, water surface tension is surpassed only by mercury. You can see this property in action when you carefully overfill a glass of water and watch the surface bulge upward in a dome shape, held in place by the cohesive forces between water molecules at the surface. You can see it when small insects walk across the surface of a pond, supported by a film of water molecules clinging to each other so tightly that the insect weight cannot break through. You can see it in the way water droplets beat up on a wax car hood, forming nearly perfect spheres rather than spreading flat. And you can see it, or rather its consequences, in every plant on Earth, because surface tension, combined with the related phenomenon of capillary action, is what allows plants to transport water from their roots to their leaves, defying gravity in the process. A giant redwood tree in Northern California can stand over 300 feet tall, and water must travel from its roots, deep underground, all the way to the needles at its crown. There is no mechanical pump inside a tree. Instead, the tree relies on a combination of surface tension, cohesion between water molecules, and adhesion between water molecules and the walls of the tiny vessels called xylem that run through the trunk. As water evaporates from the leaves, a process called transpiration, it creates a negative pressure that pulls the column of water upward through xylem, molecule by molecule in an unbroken chain. This chain holds together because water molecules cling to each other with such remarkable tenacity. Their mutual attraction strong enough to support a continuous column of water stretching hundreds of feet into the air. If water had the surface tension of, say, ethanol or acetone, this mechanism would fail. The water column would break, air bubbles would form in the xylem, and the tree would be unable to hydrate its upper reaches. Forests as we know them, towering ecosystems that shelter countless species and regulate atmospheric chemistry, exist in part because water molecules are unusually sticky. And then there is water's role as a solvent, a role so central to chemistry and biology that water has been called the universal solvent, though this title, while not entirely accurate, captures something essential about its character. Water can dissolve a wider variety of substances than any other common liquid. Salts, sugars, amino acids, gases, minerals, acids, bases. The list of materials that water can dissolve, or at least partially dissolve, is staggering. When you stir a spoonful of table salt into a glass of water and watch it disappear, you are witnessing the relentless chemical diplomacy of water molecules at work. Each water molecule, with its positive hydrogen ends and its negative oxygen end, acts like a tiny magnet. When a crystal of sodium chloride encounters water, the water molecules surround each sodium ion with their negative oxygen ends pointing inward, stabilizing the positive charge of the sodium, while simultaneously surrounding each chloride ion with their positive hydrogen ends pointing inward, stabilizing the negative charge of the chloride. The water literally pulls the crystal apart, ion by ion, and wraps each freed ion in a stabilizing cage of oriented water molecules. The salt dissolves. This process, called hydration, is a fundamental mechanism by which water dissolves ionic compounds, and it extends to a vast array of other substances as well. Water's polarity allows it to interact with any molecule that carries any degree of electrical asymmetry, which includes most biologically relevant molecules. In your bloodstream right now, water is dissolving and transporting oxygen, carbon dioxide, glucose, hormones, electrolytes, and countless other substances to every cell in your body. Inside those cells, water serves as a medium in which all biochemical reactions take place, from the replication of DNA to the production of ADP to the folding of proteins into their functional shapes. Without water's solving capabilities, the chemistry of life would grind to a halt. There would be no way to transport nutrients into cells, no way to carry waste products out, no way to maintain the delicate chemical balances that keep cellular machinery running. If water were a non-polar liquid like oil, repelling charged particles rather than embracing them, the entire biochemical apparatus that sustains every living organism on this planet would be impossible. Life as we know it is a water-based phenomenon, not just because organisms happen to contain water, but because water's unique chemical properties are the very foundation upon which biological chemistry is built. Having now surveyed the major anomalies of water, having seen how its density behavior protects aquatic ecosystems, how its high boiling point keeps the oceans liquid, how its specific heat moderates the climate, how its latent heat of vaporization cools our bodies and drives weather, how its surface tension enables plants to grow tall, and how its solvent power makes biochemistry possible, the obvious and pressing question becomes, why? Why does water behave this way? What is it about the H2O molecule that endows it with properties so radically different from those of other substances with similar molecular weights and compositions? The answer lies in the microscopic world of molecular interactions, in a type of chemical bond that is not quite a full bond but far more than a casual acquaintance between molecules, a bond that is in many ways the most important intermolecular force in all of nature. It is called the hydrogen bond, and it is the secret engine that drives virtually every one of water's extraordinary behaviors. To understand hydrogen bonding, you first need to understand the structure of the water molecule itself. A single water molecule consists of one oxygen atom covalently bonded to two hydrogen atoms. The oxygen atom is much more electronegative than the hydrogen atoms, meaning it pulls the shared electrons in each covalent bond closer to itself. This creates an uneven distribution of electrical charge within the molecule. The oxygen end of the molecule carries a partial negative charge, while each hydrogen end carries a partial positive charge. The molecule is bent, not linear, with an angle of about 104.5 degrees between the two hydrogen atoms, giving it its characteristic V shape. This combination of charge asymmetry and molecular geometry makes water a strongly polar molecule, essentially a tiny electric dipole, a miniature magnet with a negative pole at the oxygen and positive poles at the hydrogens. Now imagine billions of these tiny molecular magnets crowded together in a glass of water. The positive hydrogen end of one molecule is electrostatically attracted to the negative oxygen end of a neighboring molecule. This attraction is the hydrogen bond. It is not a true chemical bond in the sense of shared electrons. It is more of an electrostatic attraction, but it is remarkably strong for an intermolecular force, roughly 10 times stronger than the van der Waals forces that hold together molecules of substances like methane or propane. Each water molecule can form up to 4 hydrogen bonds simultaneously, 2 through its hydrogen atoms and 2 through the lone electron pairs on its oxygen atom. When water molecules come together, they create an extensive three-dimensional network of hydrogen bonds, a web of interconnected molecules that gives liquid water properties far beyond what its tiny molecular size would suggest. This network is the reason water has such a high boiling point, because to boil water, you do not just need to give individual H2O molecules enough energy to escape into the gas phase. You need to tear them away from a tenacious web of hydrogen bonds that is constantly pulling them back. It is the reason water has such a high specific heat, because a large portion of the heat energy you pump into water goes not toward speeding up the molecules, but toward breaking and rearranging hydrogen bonds. It is the reason ice floats, because when water freezes, the hydrogen bonds lock the molecules into a rigid hexagonal lattice with more space between molecules than the disordered liquid state. And it is the reason water has such high surface tension, because molecules at the surface are pulled inward by the hydrogen bond network, creating a taut molecular skin. The hydrogen bond network in liquid water is not static. It is a seething, dynamic, constantly reconfiguring web of connections that changes on timescales almost too fast to comprehend. A single hydrogen bond between 2 water molecules lasts, on average, only about 1 to 10 picoseconds, where a picosecond is 1 trillionth of a second in the time it takes you to blink your eyes. The hydrogen bond network in a glass of water has been completely rearranged trillions upon trillions of times. Water molecules are in a state of perpetual social flux, forming bonds with one neighbor, breaking them a fraction of a nanosecond later, spinning around, and forming new bonds with different neighbors. Scientists sometimes describe this as a dance, a frenetic molecular dance in which partners are constantly being exchanged. Alliances formed and dissolved in an endless whirl of motion and interaction. This dynamism is crucial because if the hydrogen bond network were rigid and permanent, water would behave like a solid, too stiff and structured to serve as the fluid medium that life requires. And if the hydrogen bonds were too weak and short-lived, water would behave like a weakly interacting liquid, evaporating too easily, unable to maintain the cohesion needed for surface tension and capillary action. The beauty of water lies in this balance, strong enough to give the liquid remarkable structural integrity, but fluid enough to allow constant molecular rearrangement. It is a balancing act that makes water simultaneously cohesive and mobile, viscous enough to stay put but fluid enough to flow, a contradiction that turns out to be exactly what is needed for the chemistry of life to function. There is an even deeper level to the mystery of water, one that takes us into the realm of quantum mechanics, the branch of physics that governs the behavior of matter at the smallest scales. The hydrogen atoms in water are extraordinarily light, the lightest atoms in the periodic table. And this lightness has consequences that extend beyond classical chemistry. At the quantum level, particles do not have definite positions and momenta in the way that everyday objects do. Instead, they exist as probability distributions, smeared out across a range of possible states. Their behavior governed by wave functions rather than deterministic trajectories. For a particle as light as a hydrogen nucleus, a single proton, these quantum effects are not negligible even at room temperature. In the context of water, this means that the hydrogen atoms participating in hydrogen bonds are not sitting still in fixed positions between oxygen atoms. They are quantum mechanically delocalized, spread out over a range of positions, vibrating with zero-point energy that persists even at absolute zero, and occasionally undergoing a phenomenon known as quantum tunneling, in which a proton passes through an energy barrier that, according to classical physics, it should not have enough energy to surmount. This tunneling effect means that hydrogen atoms in water can sometimes hop from one oxygen atom to a neighboring one, briefly breaking one hydrogen bond and forming another in a way that defies classical expectations. Researchers have proposed that these quantum effects play a meaningful role in determining water's properties. In 2022, experiments using ultra-fast laser spectroscopy captured evidence of quantum mechanical energy transfer between neighboring water molecules, a kind of quantum tug-of-war in which the hydrogen bond momentarily contracts before releasing energy, a process that helps redistribute thermal energy through the liquid in ways that classical models alone cannot explain. The quantum nature of water's hydrogen atoms may also help explain why water's properties are so sensitive to isotopic substitution, a clue that has fascinated scientists for decades. This brings us to one of the most striking demonstrations of quantum effects in water, the curious case of heavy water. Heavy water, or D2O, is chemically identical to ordinary water except that each hydrogen atom is replaced by deuterium, an isotope of hydrogen that has one neutron in addition to the single proton found in normal hydrogen. This makes deuterium roughly twice as heavy as ordinary hydrogen, but chemically, it behaves almost identically, forming the same types of bonds and participating in the same reactions. If water's properties were determined solely by classical chemistry, you would expect heavy water to behave almost exactly like regular water, but it does not. Heavy water freezes at about 39 degrees Fahrenheit instead of 32, a difference of 7 degrees. Its density is about 10% higher than that of ordinary water, so ice made from heavy water sinks rather than floats. Its viscosity is measurably different, its boiling point is slightly higher, and its biological effects are dramatically different. Living organisms that are given heavy water instead of ordinary water experience metabolic disruption and, in sufficient concentrations, death. Cells that run on ordinary water cannot run on heavy water because the slightly different quantum mechanical behavior of the heavier deuterium nuclei alters the rates of enzyme-catalyzed reactions, disrupts the folding of proteins, and interferes with the delicate molecular machinery of life. The fact that simply doubling the mass of the hydrogen atom, without changing anything else about the molecule's chemistry, can have such profound effects is powerful evidence that quantum mechanical phenomena, particularly the zero-point energy and tunneling behavior of the proton, play a significant role in determining the properties of ordinary water. In a very real sense, the water in your glass is a quantum mechanical substance. Its behavior is shaped not just by the classical forces between molecules, but by the wave-like, probabilistic nature of the lightest atom in the universe. Having explored the molecular and quantum underpinnings of water's strangeness, let us now dramatically expand our scale of inquiry and consider water's place in the cosmos, because water is not merely a terrestrial phenomenon. It is a universal one, found throughout the observable universe in quantities that stagger the imagination. The ingredients for water, hydrogen, and oxygen are two of the most abundant elements in existence. Hydrogen is a primordial element, forged in the first minutes after the Big Bang, making up roughly 75% of all ordinary matter in the universe by mass. Oxygen is produced in the nuclear furnaces of massive stars and scattered into space when those stars explode as supernovae. Given the cosmic abundance of these two elements, it is perhaps not surprising that water molecules form wherever and whenever conditions allow. But the sheer scale of water's presence in the universe is nonetheless astonishing. In the vast molecular clouds that float between stars, clouds of gas and dust that serve as the nurseries where new stars and planets are born, water exists in the form of ice grains coating tiny dust particles and has faint traces of water vapor. In the disks of material that swirl around newly forming stars, water is a major component, already present before planets have even begun to coalesce. In the atmospheres of giant exoplanets orbiting distant stars, the spectral signature of water vapor has been detected by space telescopes, confirming that water is a common atmospheric constituent across the galaxy. And in one of the most jaw-dropping astronomical discoveries of recent decades, scientists in 2011 found the largest reservoir of water ever detected, a cloud of water vapor surrounding a quasar, an actively feeding supermassive black hole, located about 12 billion light-years from Earth. This cloud contained an amount of water equivalent to 140 trillion times the volume of all of Earth's oceans combined. And this water existed when the universe was only about 1.6 billion years old, barely a tenth of its current age, demonstrating that water has been a feature of the cosmos almost from the beginning. Closer to home, our own solar system is drenched in water. Earth is the obvious example, with its vast oceans covering nearly 71% of the planet's surface. But water is found on or within nearly every major body in the solar system. Mars has water ice locked in its polar caps and buried in its subsurface soil. And there is compelling evidence that liquid water once flowed across the Martian surface billions of years ago, carving the river valleys and flood channels that are still visible today. Jupiter's moon Europa is encased in a shell of ice beneath which lies a global ocean of liquid salt water, kept liquid by the tidal flexing caused by Jupiter's immense gravity. This subsurface ocean may contain more than twice the volume of water in all of Earth's oceans. Saturn's small moon Enceladus has been observed shooting geysers of water vapor and ice particles into space from cracks in its icy surface, direct evidence of a subsurface ocean being heated by geothermal activity. Even tiny, distant Pluto shows signs of subsurface water ocean. Comets, those icy wanderers of the outer solar system, are essentially dirty snowballs, composed largely of water ice mixed with dust and organic compounds. And asteroids, particularly those in the outer asteroid belt, contain significant amounts of water locked within hydrated minerals. NASA and other space agencies are intensely interested in these water-bearing bodies, not only for what they can tell us about the history of the solar system, but for a far more tantalizing reason: the possibility that where there is water, there might also be life. The connection between water and life is so fundamental that it has become the guiding principle of astrobiology, the scientific search for life beyond Earth. The mantra of astrobiologists is simple and direct: follow the water, wherever liquid water exists. The conditions for life as we know it are at least potentially present. This is not mere speculation. It is grounded in everything we know about how life works on Earth. Every known living organism, from the simplest bacterium to the largest whale, depends on liquid water for its survival. Cells are essentially bags of water in which the molecular machinery of life operates. The chemical reactions that power metabolism, replicate DNA, build proteins, and transmit signals between cells all take place in aqueous solution. Remove the water, and these reactions stop. The cell dies. The organism dies. There is no known form of life that can actively grow and reproduce without liquid water. Some organisms can enter a state of suspended animation when water is unavailable. Bacteria forming endospores, tardigrades entering a desiccated state called ton, seeds lying dormant in dry soil, but these are survival strategies, not active living. The moment water becomes available again, life resumes. Water is not just a passive backdrop against which life happens. It is an active participant in the chemistry of life, a reactant in photosynthesis and hydrolysis, a product of cellular respiration, a structural component of proteins and nucleic acids, a thermal regulator, a transport medium, and a protective solvent all at once. The reasons why water is so uniquely suited to supporting life read like a summary of everything we have discussed. Its solvent properties allow it to dissolve and transport the nutrients, minerals, and signaling molecules that cells need. Its high specific heat protects cells from rapid temperature fluctuations that would denature proteins and disrupt metabolic processes. Its high latent heat of vaporization enables organisms to regulate their body temperature through evaporative cooling. Its wide liquid temperature range means that habitable environments can exist across a broad spectrum of planetary conditions. Its anomalous density behavior ensures that aquatic ecosystems survive winter freezes. Its surface tension and cohesive properties enable the capillary action that allows plants to draw water from their roots to their highest leaves, supporting terrestrial ecosystems that shelter and feed countless species. Each of water's anomalies, each violation of chemical normalcy that we have cataloged, turns out to have a direct and often critical role in making life possible. It is as though water were custom designed for biology, though of course the reality is the reverse. Life evolved to exploit the unique properties of the medium it found itself in. Billions of years of evolution have shaped every organism on Earth to take advantage of water's quirks, to the point where life and water are so deeply intertwined that separating them is essentially impossible. Some scientists have gone so far as to argue that water's properties are not just necessary for life, but are, in a sense, the template on which life is patterned, the molecular environment that constrained and directed the evolution of biochemistry from the very beginning. This raises a profound question about the origin of Earth's water. Where did it come from? The answer, it turns out, is even more remarkable than you might expect. For decades, scientists debated whether Earth's water was delivered by comets and asteroids bombarding the young planet in its early history, or whether it was present in the dust and gas from which the Earth originally formed, trapped within the minerals that accreted to build the planet. Recent research has provided a surprising twist. A significant portion of Earth's water may be older than the solar system itself. Studies of the deuterium to hydrogen ratio in Earth's water, compared to the ratios found in various solar system objects and in the interstellar medium, have revealed that the water on Earth cannot all be accounted for by processes that occurred within the solar system. A substantial fraction, possibly 30 to 50% or more, appears to have originated in the cold, dark molecular cloud that existed before the sun and its planets formed. This interstellar water, formed on the surfaces of tiny dust grains in the frigid reaches of space, was incorporated into the solar nebula, the rotating disk of gas and dust from which our solar system condensed, and eventually found its way into the growing Earth. The implication is staggering. When you drink a glass of water, some of the molecules in that glass may have been floating in interstellar space before our sun was born, older than the solar system by millions of years. Ancient travelers that survived the violent birth of a star and its planets to end up improbably flowing from your kitchen faucet. The water in Earth's oceans was also likely supplemented by deliveries from comets and water-rich asteroids during the period of heavy bombardment that scarred the young Earth and Moon with impact craters. Regardless of the precise proportions, the fundamental point is clear. Earth's water has a cosmic pedigree. It came from space, and it was this cosmic water, delivered to a rocky planet at just the right distance from its star, that filled the oceans and set the stage for the emergence of life. If water is abundant throughout the universe, and if water is the essential ingredient for life, then the natural question, the one that every astrobiologist and every curious person eventually asks, is whether life exists elsewhere. The honest answer is that we do not yet know, but the conditions appear to be favorable. The discovery of liquid water oceans beneath the icy surfaces of Europa and Enceladus has electrified the scientific community. Because these oceans exist in environments that may provide everything life needs: liquid water, chemical energy from hydrothermal vents on the ocean floor, and the raw chemical ingredients for biochemistry. NASA's missions to these moons, planned and in development, are explicitly designed to search for signs of life, whether in the form of organic molecules in the geyser plumes of Enceladus or in the composition of Europa's surface ice. Beyond our solar system, the search for habitable exoplanets focuses on the habitable zone, the range of distances from a star within which a planet could maintain liquid water on its surface. Thousands of exoplanets have been discovered, and dozens of them orbit within their star's habitable zone. Some of these are rocky planets roughly the size of Earth, and as our telescopes grow more powerful, we are beginning to analyze the atmospheres of these distant worlds, searching for the spectral fingerprints of water vapor and other molecules that might indicate habitability or even biological activity. The James Webb Space Telescope and its successors are tools purpose-built for this search, and the early results are tantalizing, with water vapor detected in the atmospheres of several exoplanets. We are living in an era when the question of whether life exists beyond Earth is transitioning from philosophical speculation to empirical investigation, and water is at the center of every search strategy. When you step back and consider the full picture, the story of water is nothing less than the story of the universe itself, told through the lens of a single molecule. Hydrogen atoms forged in the Big Bang, combined with oxygen atoms forged in the hearts of dying stars to create H2O, a molecule of astonishing simplicity that, through the magic of hydrogen bonding and quantum mechanical effects, exhibits a suite of physical properties so anomalous, so far removed from what its molecular weight and composition would predict, that it creates the conditions for liquid oceans, stable climates, and ultimately the emergence and sustenance of life. Water shapes the geology of planets, carving canyons, eroding mountains, depositing sediments, and driving the plate tectonics that recycle Earth's crust. Water shapes the atmosphere, driving weather patterns, forming clouds, and distributing heat from the equator to the poles. Water shapes biology at every scale, from the folding of a single protein molecule to the migration patterns of whales across ocean basins. And water connects the cosmic to the personal in a way that no other substance can, because the water molecules in your body have a history that stretches back to the interstellar clouds that predated our solar system, through the fiery accretion of planets, through billions of years of cycling between ocean and atmosphere and ice cap and living cell, to the glass sitting on your desk right now. Throughout human history, long before science could explain any of this, people recognized the specialness of water. In mythologies and religions across every culture, water appears as a symbol of purification, renewal, creation, and destruction. Ancient civilizations built their cities along rivers, worshipped water deities, and developed elaborate irrigation systems that transformed deserts into farmlands. Philosophers from the ancient Greeks onward pondered the nature of water, with Thales of Miletus famously proposing that water was a fundamental substance from which all things arose. An intuition that, while not literally correct, captured something true about water's centrality to the natural world. Modern science has vindicated that ancient reverence, not through mysticism, but through the painstaking accumulation of evidence showing that water is, in measurable and quantifiable ways, the most remarkable substance we know. And yet, despite centuries of study, water still holds mysteries. The exact nature of the hydrogen bond network in liquid water, the detailed mechanisms of water's behavior at interfaces and in confined spaces, the role of quantum effects in biological water, the possibility of liquid-liquid phase transitions. These and many other questions remain active areas of research, attracting some of the brightest minds in physics, chemistry, and biology. Water, the most familiar substance on Earth, is also one of the least fully understood, and every new discovery seems to reveal further layers of complexity hidden within its transparent simplicity. So the next time you pour yourself a glass of water, pause for just a moment, look at it, hold it up to the light. Consider that this clear, odorless, tasteless liquid is a substance born from the ashes of dead stars and the primordial hydrogen of the Big Bang. Consider that its molecules are engaged in a frantic, beautiful dance of forming and breaking hydrogen bonds trillions of times per second, a quantum mechanical ballet that gives this liquid its extraordinary properties. Consider that the ice floating in your drink is performing a feat that almost no other solid in the universe can manage, defying the normal relationship between solid and liquid density, a trick that has kept aquatic life alive through every ice age this planet has ever endured. Consider that the warmth of the water flowing from your tap would be impossible if water did not have an inexplicably high boiling point, an anomaly that keeps the oceans liquid and the planet habitable. Consider that every cell in your body is a water-based chemical factory, utterly dependent on water's solvent properties, its thermal stability, its surface tension, and its capacity to facilitate the biochemical reactions that keep you alive. Consider that the same substance, the same H2O, exists in unimaginable quantities throughout the cosmos, in interstellar clouds and comet tails and the subsurface oceans of distant moons, and that wherever it is found in liquid form, it carries with it the potential for life. A single glass of water contains all of this: cosmic history, quantum mechanics, biological necessity, and planetary-scale environmental regulation, all packed into a substance so common and so transparent that we barely give a thought. Water is, without exaggeration, the most extraordinary ordinary thing in the universe. It is a miracle hiding in plain sight, the anomaly that makes everything else possible, the quiet, unassuming substance that has been shaping the cosmos, sculpting the earth, and sustaining every living thing for billions of years. And it is right there in your glass, waiting for you to take a sip,